This is a talk that I am really excited about because ever since that we have been in this YouTube space, people are like, have you seen this channel? See the pattern? And I remember looking at Gareth's channel when we first started out and we had, 100 subscribers. And I'm like, man, this guy is good. And it was just such a cool template for being able to take super, super complex ideas, break them down into digestible pieces, and lay them out in a way that is not dogmatic, it is dispassionate, produced in an excellent accent, and just deeply curious. And so I'm sure that this talk is no different because we will explore what will it take, and there's no one better to lead us down this path than the man himself, Gareth Samuel.
The scientific revolution starts now.
DemystifySci podcast.
Let us see in the dark. I think I'd like to start by saying it is an unusual honor to be here. I'm not like the other speakers in that sense. I'm not presenting a theory. I'm not here necessarily advocating for one model over another. It's about trying to understand the universe we live in. And some of you will obviously know me from See the Pattern, where I look at alternative theories in physics, cosmology, and beyond. But today, I'm going to do something a little bit different. This is not This is not a talk about one theory or another. This is about fundamentally asking the question, why is it that it's so difficult to challenge the framework that we use to understand the universe? Okay, and I want to start with a confession, loosely borrowed from Tolkien, and probably more in truth than in jest. And that is that I know half of the alternative theories half as well as I'd like, and I probably like half as many as I probably deserve. But the reason that I'm here is because I believe that those alternative ideas deserve a seat at the table. There is value in understanding even broken and half-baked concepts because they might spark other ideas. And that's really the spirit of the talk. It's not to compare one thing or another. It's to ask the question, what happens when the system that we've built to understand the universe attempts to preserve itself more than seek the truth? And the way that I'm going to do this is split the talk into a number of sections. So we're going to start by discussing the limitations of the data that we actually receive. Then we're going to look at how models end up being produced and how they can create cyclic loops that can become dangerous. And then we're going to look at why I think the problems are bigger than just cosmology, that if you want to solve it in a different way. And then lastly, the human aspect, which I think is also an important point. But let's start by, in essence, framing the challenge. Now, it's often said that the biggest challenge in science is that we need better machines, we need better precision, we need more data. But what if the question is not what we see, but how we've learned to see it? We inherit the frameworks that we use to understand and interpret the data, the universe, and those frameworks shape the data into what is considered probable, precise, and real. But what if the question isn't about whether there is a better story, but whether the act of storytelling itself is where the problem lies? And I think part of the problem is that if we don't examine the lens through which we see the universe, then we risk taking the limit of our vision for the limit of reality. And that's a danger, I think. But let's start by asking a simple question. And this is probably something that a lot of us just take for granted. And that is, what is it that we do when we say that we're doing astronomy? And essentially, what we're attempting to do is to reconstruct a dynamic three-dimensional universe, but understanding that what we're actually receiving are two-dimensional images, like shadows cast on our detectors. It's as if we're if you were to look at a sculpture and I was limiting you to only look at the shadow of the sculpture, from that shadow, you can infer certain properties. You could infer its texture, you might be able to infer its depth, and you might be able to infer its motion, but all the while understanding that you never have access to the full three-dimensional structure of the sculpture. So that's just a limitation of what we have. And I guess another point is that it's true to say that we don't observe the universe, we observe light from the universe. And I think that's an important distinction to understand. Now, when we do receive light or the data from the universe, we're in most parts restricted to a very small subset of what the universe contains. The electromagnetic spectrum is the prime messenger that we use to make sense of the universe. And, we've built incredible machines to be able to detect gamma, infrared, visible light. But everything that we know is filtered through that one channel, whether it's at the birth of a star, whether it's looking at how galaxies exist. I'm not going to say evolve because that's a different question. The CMB, it's all filtered through that same channel primarily. And essentially, they're different frequencies of the same underlying phenomenon. So if there are processes that occur in the universe that don't interact with light or that emit things that we cannot detect through light, then we might never know about them. They would be inaccessible to our understanding. Now, the next problem is that when we do receive images, that they are snapshots in time. Because light travels at a finite speed, it means that the objects that we observe are objects that occurred in the past. We're never seeing the present, we're always seeing the past. So when we look at a galaxy, we don't see a galaxy evolve. Our lifespans are so short that we can never experience the beginnings and the ends of a galaxy. We just see snapshots of that galaxy. So then you might ask the question, well, how do we then determine how the galaxy evolves? And that is done by stitching together different images of different galaxies at different redshifts and assuming or inferring a galactic evolution from that. But it's a bit, I like analogies. So it's a bit like if you were an alien visiting the Earth and you were only given a very short period of time to assess the average lifespan of a human, but they gave you access to all the images on the internet, and you built an algorithm that was able to filter and select humans that had a similar characteristic, and from it you generated what you think the average life cycle of a human is. It's not necessarily correct, but you're inferring a connection between different images because the images are not necessarily the same person because you only have that snapshot. So it's a limitation you have to understand when we look at how we think that galaxies evolve, in terms of what we do with it. So the next question is, well, when we do receive the data, what can we actually measure about it? And the reality is we're quite limited in what we can measure. So directly we can measure things like photon flux, spectral lines, its angular position in the sky, polarization, raw timing. There's a sequence of things that we can directly measure from the instrument. But there are a lot of other properties that we have to infer: distance, intrinsic luminosity, temperature, age, curvature, etc. And the thing to understand is that you don't get to those inferred characteristics without applying a model. Some models are more complex and some models are simpler. So a redshift doesn't become a distance until you assume a cosmology. So the raw data doesn't speak for itself. It has to be processed. We filter it, we correct it, And therefore, that's all done through a theoretical lens. Yeah, we apply that to the model. That processes the raw data based on what we think the model expects it to be. So we often talk about the universe revealing itself to us, but in effect, what we're doing is constructing a picture of that universe. We subtract foregrounds, we smooth the noise, we calibrate the instruments, all based on model expectations. So our vision of the cosmos is not a photograph, it's constructed and guided through theories that we believe in. And I'm not saying there's anything necessarily wrong with that. That is the nature of science at this scale. But you have to understand that if the model is wrong, then the universe that we create using it is also wrong. So let's move on and talk about how models are then built and used to process the data. It's nice to think that the cosmological model is built up gradually on firm observational grounds. But the reality is that in order to even start processing the data, you have to start making assumptions early on. Yeah, so redshift is seen through an expansion lens. We don't physically observe space expanding, yeah, but we see the redshift and assume that within an expansion model. The CMB is assumed to be from a hot, dense origin, but we don't have unambiguous proof of its age. We detect the radiation, and that radiation fits what we expect from the model. But if you take the same data and you process it through different assumptions, then what you generate is a universe that might look entirely different to the one that you have under the Lambda CDM. So the models interact with the data. You take ideally, what you would like to see is you take the raw data, you test it against a whole series of different models, and then you make a decision which model is best. But the reality is, even to start processing the data, you have to involve a model. So right from the beginning, it's used to clean the data, to prepare it. The model constructs the data. It guides you into what decisions you make in terms of what's signal and what is noise. And it in essence, the model shapes the data, and then the data aligns with the predictions. And it's essentially the model is framing the rules of interpretation for the data. So you can end up with self-reinforcing loops. And I'm not saying that's necessarily a conspiracy. That's just what happens when you have deeply embedded assumptions in your model. But there's a danger in that, because when those assumptions are so deeply embedded, you become blind to alternatives, because the entire ecosystem from instrument to analysis pipeline is designed for that particular model. And other models struggle to be able to interpret that data in a way that makes sense for them. It's not impossible, but it's harder to do. Now, I was going to talk about, give examples of redshift and CMB, but I think we've probably already discussed that enough. So I'm going to, for the sake of brevity, skip over those. But I just want to come back to this slide, because a lot of people have mentioned it, that the CMB is a cornerstone. I think it's just important to understand that the CMB is also used as evidence in other parts of the model. Yeah, so dark energy, dark matter are inferred from data in the CMB. So therefore, if the CMB were to fall, then that's a large part of the pillar that collapses with it. So why does it matter? I think if the models we use become the lens through which we do all the data processing, then there is a big risk that our model stops being testable. Because the model rules determine how we clean the data, and then when the data confirms the model, any contradiction to that model is then assumed to be an incomplete understanding, and we introduce a patch. Those patches can then become essential truths, and they become untouchable because they're required to maintain the internal consistency of the model. And this is why it matters, I believe, because if you constantly patch the model and you never stop to question it, then it can't ever be wrong, no matter what the data says. And in my mind, that's not science, that's doctrine. Now, we've talked about some of these already, the patches that were introduced, so I'm not going to spend too much time discussing them, but I'd just like people to realize an important point. When we talk about cosmology, its main currency is light. And the only thing that creates and interacts with light is matter. And so when we look at our universe, or the universe in the lambda cold dark model, 75% of the universe is dark energy. And we end up with a universe that has less than 5% matter. So 95% of the universe in that model is made up of unverifiable elements that don't interact with light. So that, in my mind, is a concern. And the problem is that the more the model tears, the more patches we add onto it. And we're going to talk about the one at the bottom in a second, because obviously in the James Webb Telescope, they are finding younger and younger galaxies. So one of the ways to fix that is to say, well, okay, well, the galaxies must have formed quicker, quicker star formation, forming at a not necessarily earlier period, but just in a quicker time to get to that point that we see. But then the question becomes, what happens when you introduce a patch that breaks the foundation of your model? Which is exactly what may have happened. Like, it's a paper, it's not necessarily, doesn't mean it's truth. But there was a paper published recently that asked that simple question. If we are assuming rapid galaxy formation, then there is a consequence to that. And the consequence is that that extra radiation produced by those stars, reprocessed by the dust, and then stretched by expansion, should contribute to a component of the CMB. And they did an analysis of the data, and they came up with two models, a conservative model and, I suppose in their mind, an aggressive model. And the conservative model estimated that about 1.4% of the CMB could be from this background radiation from galaxies. And in their aggressive case, it was 100%. So even, because you might look at it and go, well, 1.4%, that's fine. But that's still a problem for the model, because 1.4% means that the signal that you claim to be pristine is not actually pristine anymore. And this creates a bit of a problem, because generally the scientific method is you take a hypothesis, you make a prediction, you test it, and you either validate it or you refute it. But in cosmology, it works slightly differently. We find a contradiction, you generate some kind of patch that fixes it, and then you test that model based on that patch, and it's considered an automatic confirmation. And that makes it unfalsifiable. But then the question becomes, well, what happens if you then want to create an alternative theory? You basically have two choices. You either end up accepting the patches that were introduced, you accept dark energy, you accept dark matter, but that can constrain you. You're limited in terms of the innovation you can put in it to explain things in a different way. If alternatively you choose to reject those and say, I don't agree with those assumptions, then often you're not taken seriously and you don't get a foot at the table. But I think from the discussions we've had so far, it's also evident that if you do want to explain the universe in a different way, it requires thinking that goes beyond just simple cosmology. So I think the problem is bigger than just simply we need to replace the Big Bang. Because in order to replace the Big Bang, you have to go somewhere else. And it's the difference between the cosmic scale and the quantum scale. So the main currency in cosmology, as I've already said, is light. And we know that light is created by matter and interacts with matter. So therefore, the relationship between how matter does that happens at a quantum level. So if you're going to describe different ways that that interacts, you need to consider quantum effects or look at it in a different way. The second thing is that the matter itself, so the 5% of matter, has to have come from somewhere. And therefore, you also need to be able to explain the nucleosynthesis in your model, which will also be at the quantum scale. And then lastly, we also know that light travels across the universe. So therefore, the question becomes, what is the universe itself made of? So those are all fundamental questions that are important to consider when looking at exploring an alternative. Now, it's often presented that redshift is a done deal. We know that it comes from expansion. But if it doesn't come from expansion, and we've already seen many discussions over the weekend on this, then you have to have a mechanism. There has to be some way that you're proposing that that might work. And the problem is, as soon as you start even addressing some of these ideas, like tired light, some sort of a field coupling, or even intrinsic properties that could cause it, you're stepping outside of the bounds of what is considered acceptable science. And that's much harder to do then. But I think one of the things to understand here is that if we do entertain some of those alternative ideas, then the way that we see light in those models changes, not just see light, but see light and its journey changes the way that we see the universe. And maybe we'll realize that when we're looking at the sky, actually what we're seeing is a different picture. Now, the second problem comes down to the atomic scale. So there's in the Big Bang, obviously there is the idea of nucleosynthesis right at the beginning to make some of those early elements, which then get spread across the universe. Then we have stars that reprocess it and increase the metallicity over time. And generally speaking, when you look at the abundance ratios across the universe, it does match fairly well with those predictions. Now, there are anomalies that we've discussed. The thing is that there are stars, certain types of stars, where the nucleosynthesis doesn't quite work. There are anomalies that you detect. So the question then becomes, are there alternative processes that are going on that we are unaware of? If we look at lab results, then we do see that there are anomalous results, particularly if you're looking at Lena experiments. There is evidence to suggest that we don't fully understand nuclear reactions. And therefore, the question becomes, are there other areas in space where nucleosynthesis takes place that we are unaware of, that we are not taking into account because they're not high energy? They don't produce the same radiation you see from stellar environments. But the question also becomes that if you decouple from a Big Bang and you don't end up with an origin point, you create a secondary problem, which is if the universe is infinite and has existed forever, you need a process that allows you to recycle the elements, because otherwise you would end up with a universe that is constantly being enriched. And therefore, we either just happen to live at a very privileged time in the universe that happens to have the ratios we have, or else you have to come up with a way that allows you to break the elements downwards. And that is not as easy as you think. Like, to get to all the way back to hydrogen is more complicated to do. So again, you need to think of alternative ideas that allow you to achieve that. And the structured atom model may provide some insights into that. And there are other theories as well that may provide insights into that. The thing is that it's not just about cosmology. If you want to fix this, if you want to essentially move beyond the Big Bang, I believe you have to address the two different realms. And I think that's why it's been so difficult to do, because it's not just about finding a better story for the Big Bang. I think if you want to address the Big Bang, you have to address aspects that touch on quantum mechanics as well. And that makes the problem much, much harder to do. And that's why I believe it's very difficult to replace it, the Big Bang at this point, because you're fighting two domains rather than one domain. But there are also institutional and uh, other barriers that stop us from doing that. If we consider that, so we looked at the fact that data forms loops, the way models create data can create circular referencing loops, self-reinforcing loops. But the same also happens in academia. And this is not, I'm not saying this is a conspiracy, that's just a natural fact of the way that it works. The funding is given to research programs which offer promising ideas to look at explaining certain results in certain ways. They will run the tests and simulations, produce the data. They might find small variations or alterations. That goes into publications, which then feeds back into, eventually will feed into textbooks, which feeds into teaching, which then loops back into funding. So funding essentially creates a loop which defines credibility, it defines careers, and it defines what are considered valid questions to ask. Because if you ask a question that is not considered valid, you won't find much luck in that loop. And therefore, the problem isn't just about finding an alternative for the science part of it. It's also about realizing that you're going up against a loop that's been created in terms of funding that you don't have access to. The thing also to understand is that ecosystem also creates specialization. And many people are masters of very narrow domains. In the past, people like Newton, Maxwell, Helmholtz, Kelvin were able to fluidly move across different domains. That's not possible today. And I'm not advocating that we should move back to that. I think the scale of our knowledge now demands a silo approach. But there is a problem, because if you do want a paradigm shift, you have to be able to bridge those silos. And often the most interesting ideas tend to fall between the cracks. And there's nothing that guards against that. Science is about explaining the unexplained. It's about welcoming bold and strange ideas that need to be tested. And I think as science matured, it required boundaries between the serious and the baseless ideas. A line was drawn, and Popper's falsifiability was designed to basically test against the testable versus the untestable, the ones that have evidence or don't have evidence. And I think the label pseudoscience was invented to try and draw that boundary between evidence and non-evidence. The problem was that in the early 20th century, it was also used to purify science, to remove the religion, the philosophy and imagination from it. In the late 20th century, Carl Sagan in particular became a gatekeeper of that. And things like UFOs, ESP were considered, where there wasn't enough empirical evidence, they were ridiculed. And it wasn't always about the evidence itself, it was often also about the person involved in it as well. But nowadays, there are aerial footages which are being released showing aerial phenomena that are unexplained. Research into consciousness is happening in quantum biology and other areas. So there is a shift and a change. And you realize that some of that gatekeeping has had a negative effect in terms of the perception of some of these alternative ideas. And the irony is that Popper's falsifiability was supposed to guard against untestable claims. And yet the Lambda CDM evades falsification. So pseudoscience once warned against dogma, but now it seems to protect against it. Part of the problem as well is that disproven ideas sometimes weren't given a fair chance. They were not necessarily defeated by data, but excluded by assumption. Often they were caricatured, reduced to straw men, which didn't necessarily reflect their original. And the rejection was less about the theory and more about who had proposed it. If you were seen as fringe, often it was easier to dismiss. But I honestly do believe that flawed ideas hold value. They can provide useful metaphors, even if they're partly correct, raise interesting questions that lead you on a different path, or spark new ideas. Progress is not always about moving forwards, but sometimes it's about looking back with new eyes. Now, the sad thing isn't that alternative ideas failed, but it's that curiosity itself is being punished. Science should be about asking questions, yet it rewards conformity. We end up with safe specialization, not bold synthesis. We end up with paradigm maintenance, not paradigm shifts. Science is technically powerful, but intellectually conservative. And for me, and I've already mentioned it, what I think the missing element is not some extra spatial dimension, but it's philosophy. I think science has become all about models, simulation, and maths precision, and we've stopped asking the why and the what. We've replaced conceptual clarity with technical power. If the maths work, you accept it. Understanding is not always required. An equation sometimes is equal to an explanation. But we should be asking the why before the how. Because without it, we're building conceptual frameworks on sand. And we stop noticing that the models themselves loop back on them. I believe that science without philosophy is like saying architecture without geometry. Clarity of question must equal elegance of equation. So what do I believe it'll take to change? I think to rethink the universe, we in part have to rethink science. We need philosophical openness. We need cross-disciplinary collaboration. No single silo holds the answer. And above all else, we need cultural courage, the humility to revisit old ideas, and the strength to ask forbidden questions. Science nowadays is all about preservation, preserving careers, preserving models, preserving assumptions. But are we brave enough to reframe? Because if we don't, then if we continue to see the anomalies through the same lens, then we risk not being able to escape its distortions. Are we going to guard the castle or step outside the walls? Keep patching or rebuild? The structures that we inherit were never meant to be permanent. They're scaffolding, not truths. We need to loosen our grip, question our frame, and dare to see with fresh eyes. Because the next revolution may not come from a new answer, but from better questions. Thank you.
Absolutely. Absolutely. 1,000%.
All right, we are going to get some questions from the audience, as usual.
You mentioned en passant about the difference between the current science, where people are highly specialized, and these polymaths. And you named 4 polymaths. Newton?
I had more in the list, honestly.
No, but the ones you chose are important.
Yeah.
Newton, James Clerk Maxwell, William Thomson, and
Helmholtz.
Helmholtz.
Yeah.
What's interesting for the last 3 is they are the seismic shift in the destruction of the continental, specifically French and German scientific tradition. And this corresponds to the coming to the complete domination of the Victorian era over the rest of the world. This is the Crimean War. This is the creation of the British Raj. This is the Second Opium War. And so if you want to really properly reframe, you have to go back to before these so-called polymaths, who are in fact new gatekeepers.
Well, you know more about the history of science than I do, so you might well be right on that.
I believe that was a comment. I should have made Shiloh announce it.
All right, I'm going to ask a question and make a comment. So, and Anastasia, that's okay, right?
What the time of day is?
All right.
You've had 3. You'll have 3 talks to make comments. So let's go with questions if possible.
All right, I'll be very brief. So, why are you saying that the only way we learn about the universe is through light? I mean, it seems to me that that's arbitrarily excluding. We get cosmic rays from the universe. We have in situ measurements out, billions of miles from Earth, which is part of the universe. And we have, laboratory experiments, which can, give us a lot of knowledge about the phenomena that we're studying in the universe, because we're part of the universe right here on, in Portugal.
I don't disagree with you in terms of experiments. Absolutely. Experiments can model what you think, but in terms of what we actually receive, yes, there are cosmic rays. You are correct in that. So there are particles that we receive, but but in terms of the overwhelming data that we receive, that is light. Like, you are correct. There are, and I didn't say that it was the only one. It's the predominant one. But you are correct. There are cosmic rays, and discussions on gravitational waves. But yes, there are other things that we have.
I would just say that those others deliver because they are things that we can study close up. They deliver much more concrete and reliable information, and the tendency to ignore them, especially if they don't fit the model, is part of the problem.
Right. So specifically, you're talking about the where there's missing bits. My point is more that, generally speaking, the way that cosmology works is it's based on that light data, and I understand what you're saying, and I don't disagree with you in that respect.
Yeah, I think you're missing the mark here, but in a very nice way. So you're mentioning 5 solutions to the problem, trying to defy the title of your even closer. So you're proposing these solutions of data, interpretation, cosmology. I don't know exactly what you meant with that. Philosophy and quantum as, let's say, to balance out these things, to solve the problem of having an unfalsifiable model, right?
Not entirely. So my point is more that the models we have can create circular loops. So which means it's self-confirming. That's a dangerous thing to have. I think that when you look at alternative models, in order for them to work, often they have to explain new physics, which requires you to go into the quantum domain. And that makes the problem harder because you're not solving one thing, you're trying to solve two things at the same time. So that's my point. And I'm not proposing that this is the way to do it. I'm just pointing out, why is the problem so hard? Because you're having to go across multiple domains and you're fighting against circular loops in data and also in the academia.
But I would suggest that the solution, you gave the solution to solving this problem, which is
philosophical openness and
philosophy.
Yeah.
So if you just put a philosophical overarching theme over all of these topics, you have the solution. So quantum mechanics is necessarily not a problem because you need to go to the philosophy of quantum mechanics and then say, like, look, we have some problems there with the measurement, the wave function collapse and all these things. And these are, let's say, the starts where the points where you can start from. So my question to you is, do you agree that we can just take this to a philosophical level and solve it? That we are all philosophers of science here, that we are all searching for a similar, let's say, strategy that will ultimately lead us to the solution, because this is exactly what I will try to advocate tomorrow with the roadmap, that we go to more of a philosophical level.
It would be nice. It would be nice to think that we could. I have my doubts, but
Okay,
glad to
hear that. So also a little bit of advertisement for tomorrow. If you cannot be there, if you cannot be present at a workshop for the roadmap, don't worry, you can still be part of it, because we can also do it through email communication later on, so we can see what your input can be, whether you want to collaborate on this. So certainly check your emails after the conference also.
That was a question. That was a comment thinly veiled as a question.
I like it very much, your presentation. You touched very important topics. And among them, what I like is at the beginning, you said something important that many theoreticians do not take into account, this naive image that we have some observations or some experiments, and you can check directly your theory. You are totally right that the analysis of data, and all people working as experimentalists or observers know that there are some difficulties. We are some way model dependent. Now my question is, we have to distinguish. There are models which are directly related to cosmology, and other which are depends on other models. You have given an example, for instance, of the CMB and the subtraction of the foregrounds. This subtraction of the foregrounds does not depend on the cosmological model. It depends on the models of the galaxy, of the foregrounds and other things. And also there are other kinds of data. For instance, if you want to determine the redshift of a galaxy, this is just observing the line, the position, should be quite model independent. So possibly you can make some comments about this distinction between model dependent in the cosmology, so it's depending on a cosmological model, or is depending on our physics or other stellar physics or other things, no?
Yeah, no, you're absolutely right. So redshift as an example, when you look at galaxies, again, I also think that there's a language difference here from what I use to what cosmologists use in terms of model. Like when you look at a galaxy and you determine its redshift, the machine that you measure it off will give you a spectrum. Yeah, and you know that and obviously it's not a clean spectrum. It has all sorts of other lines, and therefore you have to make an educated assumption as to what generated that spectrum, and therefore how much it shifts based on what you think it was at, a rest speed. But that's still a model. In my mind, that's still, you're playing a model. It's a simple model, and it's not one that's overly complicated and doesn't necessarily create a circular loop. So you're correct that there are some, and I wasn't saying that everything is circular, but there are certain parts of cosmology that create circular loops that self-reinforce themselves. But you're right that not all of them do. That's absolutely correct. That there are some, but that's not to say that you are not making an assumption and you're applying a model to be able to get to redshift. And some redshifts are harder to get to than others because there might be other material in between. You have to guess what it might be, and some are clearer. So I agree with that.
All right, so I just have a quick comment. At one point, you had a slide that, of course, but at one point you had a slide where it looked like you had some atomic structure that was being revealed back from, I believe it looked like an icosahedron there. Yes, that one right there. Interestingly enough, Nick Mernes from the Wolfram Institute found that the minimal graph structure required to model qubits happened to be an icosahedron in 4 dimensions, aka the 600 cell. So that's all.
Thank you.
Yeah, this is a comment. I really welcomed your call for philosophy, because philosophy is one of my main interests. As a teenager, my mother got me reading R.G. Collingwood, and his concept of philosophy was a kind of mediator between all the different disciplines. So it would be the polymath that would go between all the different disciplines in knowledge. And he solved for himself various problems by writing about the different disciplines. And his book, The Idea of Nature, which is a history of science, is incredibly illuminating. And it's one of those 1930s type publications which is dense with information. It's not the posturing that we see in so much commercialized intellectual work that we see today. And what Collingwood, by positing philosophy as the kind of mediator between the different disciplines, I think instead of saying there's so much data no one can possibly be a polymath, I think that this we create a collective polymath by spending time talking to people in different disciplines and having the space to discuss, which is what I feel has been set up here. Collingwood was in dialogue with Alfred North Whitehead and producing. He was a scientist who Collingwood patronized him and said, "Well, you're a scientist. You've made great progress. You've gone from Plato to Aristotle." Because in the basic ideas of talking, a lot of these basic ideas have been already worked out by philosophers in the past. But their dialogue was closed down during the Second World War. What won in UK philosophy departments was analytical philosophy. And Collingwood ended up writing the Roman history of Britain. He had to become a historian. So that strand of philosophy was extinguished in British culture. It's been replaced from the 70s and 80s onwards by what's called continental philosophy, which is a strange thing because analytical philosophy is a definite kind of philosophy. Continental is defined by geography, but what it means is importing. Sorry. This belongs to the conversation space. Okay. So I'm very grateful for your talk because I feel it's opened up this discussion, which we should all be having. And yeah, thank you.
Yes. For sure.
One last question from the great and mighty Saren Leff.
Thank you. After I ask my question, can you do your outro live in person? My question is, what's the pink elephant in the room in your view? What would be?
I would say, if you're going to ask me like that, then we are the pink elephant in the room. I think the biggest obstacle to change is our own mindsets. And if I'm being honest across the group here in terms of the different presentations that are done, I think a lot of it comes down to people wanting to hold on to their own idea of what they think is right. And I guess there's a point in the reason why you defend those ideas, but sometimes you have to be slightly more fluid in order to be able to move forward. And I do see that from some people, less so from other people. And it's an interesting dynamic, the human aspect of owning and having ideas. And I guess that's part of also when you look at the Big Bang model, there's a lot of collective thought that's gone into it, which creates a momentum in itself that's difficult to change as well. But if you're putting me on the spot for one pink elephant, I would say we are all the pink elephant in this room.
I like that. We actually we have one more question. One more question.
One.
I'll try to make this a question. Could you go to your page on the solution? Just put that link up to your browser. Just
This one?
yeah. So, what do you think of the idea? I liked what Alexander Unzicker did and a few others did, which said, I have a coherent theory and I want to test it against a bunch of things, and then I have a scorecard. Eric also did that very nice with a scorecard. This doesn't really. So Shiloh made a comment one time that said, people try to be not wrong. So you have a new cool theory, but if you put it out there, it'll be different in 4 different ways, which means you could be wrong 4 different times. So they pattern match as much as possible to what everybody agrees with, so they can only have one wrong thing, right? As opposed to the theory, your new idea or something is coherent in some sense, but then it's tested against a scorecard. And this doesn't really encourage having that kind of scorecard. Like, you know what I mean? To get you out of the box a little bit. And what do you think of that idea?
Yeah, I'm not necessarily saying that this is like I'm not proposing that this is a structure that we have to adopt. What I'm pointing out is that I think that the solution encroaches on a number of different areas. That in terms of how we interpret the data, in terms of cosmology and the cosmologists themselves, the data that we get, in terms of understanding the quantum side of it, so how light propagates and the effects. If we're going for something like if you're wanting to explain redshift in a different way, you have to go to that domain as well. And then I think above all else, across the entirety of it, we have to keep asking the question of why. And I think too often that question is not asked. It's just accepted that the data supports this, therefore. And I think we need to be more mindful of making sure that we're always asking that question. So the scorecard idea,
I guess it's a technique,
but
it might help you get a different mindset.
Yeah, but that's also in some sense arbitrary, because someone else would draw up the scorecard very differently because they choose different data points that are more meaningful to them, and you would score less well on their scorecard versus the way you drew it up. So
yeah, but actually I think that would be great, because if you published your scorecard, you could also have a discussion about why do you think it's good, and it just gives it a little more exposure of the objective.
Sure, but also the question then becomes which point are you allowed to fail on? Like, because if you fail on one point, is that a problem? Or if that one point is actually the most crucial part, like how do you weigh each one of those scorecards is another. I don't think you're not wrong in it. It's a good way to approach it. It's just you have to be really mindful of how you do it.
All right, great.
Excellent. Thank you so much.
Awesome.